Welcome to the lecture series on numerical methods. So, we have discussed interpolation. Then based on the interpolation in the last lecture we have discussed about this numerical differentiation based on Newton's forward difference and Newton's backward difference approximations. So, today we will just discuss this numerical differentiation based on Lagrangian interpolation, divided difference interpolation, and then from that differentiation how we can just determine this maxima and minima of a function based on these polynomial approximations that we will discuss. So, basically we are just discussing here that whenever you will have a tabular values like xi, fi's at n plus 1 distinct points starting from 0, 1, 2 up to n, then usually this Lagrangian polynomial p n x is written in the form like p n x this equals to summation I equals to 0 to n Li x f of xi. So, or sometimes we also for our convenience we are just writing k equals to 0 to n Lkx f of xk also, where this Lkx is called the Lagrangian coefficient, and if it is interpolating with a polynomial then it is called Pnx here. This means that we are just formulating or constructing a polynomial Pnx based on this n plus 1 nodal points considering this functional values based on this function f of xk here. So, if you just write here this Lagrangian coefficient, then usually we are just writing this Lagrangian coefficient Lkx as omega x by x minus xi w dash of xi here. So, where usually this w of x is defined in the form like x minus x0, x minus x1 up to x minus xn here. Since we have here these tabular points expressed in the form of like x0, f of x0, x1, f of x1 up to xn, f of xn. Especially we are just evaluating these derivatives at the position that if the function is not known us explicitly. This means that if the tabular values has been given like x0, y0, x1, y1 up to xn, yn, where exactly this function is not known to us, then we can just also approximate this polynomial in the form of Pnx, from where or from that we can just get this differentiation of this function f of x at different points, maybe at the same tabular points or sometimes maybe at different points also, which is existing within any of the interval of these tabular points. Basically, if you will just want to evaluate this derivative for this function Pn dash or Pn of x here, the derivative of Pnx usually it is written in the form of Pn dash x here, and this can be written as summation I equals to 0 to n Li dash of x f of xi here. Since if you will just see here this omega x consists of these variables in the form of x here, where we can just differentiate this function. Especially if you will just see this derivative of p and x is nothing but the derivatives whatever it is just operating on Li of x here multiplied with this functional values or the tabular values which has been given at all of these nodal points or tabular points. If we can just write this one in a complete form, we can just write this one as L0 dash of x f of x0, L1 dash of x f of x1, since we have these known values of x0, x1 and x2 up to xn, and where also these functional values are known to us, which all are constants here. Especially it can be written of the form, since the final point is here nth point, so ln dash x f of xn, this one. So, specifically if you will just see here the slides, so we can just say that xi are the values which is expressed at all of these node points, that is in the form of x0, x1 to xn, and the functional values that is expressed in the form of f of x0, f of x1 to f of xn here. So, suppose first we will just consider a Lagrange polynomial which is used 3 points, suppose, since at a time if you will just consider n points it is difficult to understand. So, first we will just consider 3 points, suppose. If you will assume that the function goes through suppose 3 points and the points are defined in the form like x0, f of x0, x1, f of x1, x2, f of x2. Either you can just write in the form of f of x0, f of x1, f of x2, or you can just write that one as x0, y0, x1, y1, x2, y2. Sorry, this one x2, y2 here. Since we are just expressing here y equals to f of x, and if we will just consider this polynomial here, so this can just generate a polynomial of degree 2, that is in the form of p2x here, which can be written in the form of L0x, f of x0, L1x, f of x1 plus L2x, f of x2 here. And if we will just write independently all the terms here, this means that L0x can be written in the form of like x minus x1, x minus x2 divided by x0 minus x1, x0 minus x2 here. Similarly, L1x, this can be written in the form of like x minus x0, x minus x1, sorry, x minus x2 divided by x1 minus x0, x1 minus x2 here. Similarly, L2x can also be written in the form of like x minus x0, x minus x1 divided by x2 minus x0, x2 minus x1 here. So, if you will just express these 3 Lagrange polynomial coefficients L0x, L1x and L2x in this form here, then we can just write P2x as, thus P2x can be written in the form of like x minus x1, x minus x2 by x0 minus x1, x0 minus x2 into f of x0 plus x minus x0, x minus x2 divided by x1 minus x0, x1 minus x2 into f of x1 plus x minus x0 into x minus x1 divided by x2 minus x0, x2 minus x1 into f of x2 here. So, if you will just write this polynomial in this form, then easily we can just evaluate the derivatives for this function p2x here or the polynomial p2x here. So, if you will just differentiate this polynomial p2x with respect to x here, differentiating p2x with respect to x here, if you will just differentiate this one, then we can just write this differentiation as p2 dash x here. So, p2 dash x, if you will just see here, first product if you will just take, so x square, this means that we can just write 2x minus, if you will just say x is a product of here, that can just give you minus x1 here. If you will just take the product of this one also here, that will just give you minus x2 here. And last derivative if you will just consider, this is nothing but a constant here, plus x1 and x2, and its derivative will be 0 here. Then divided by all of these points, if you will just see, all are here constants. So, that is why we can just write x0 minus x1, x0 minus x2, f of x0, since all are here constants only. So, next derivative point if you will just consider here, or the next derivative term associated with this p2x, that can be written in the form like 2x minus x0 minus x2 divided by x1 minus x0, x1 minus x2 f of x1 plus the last term, if you will just differentiate, it can be written in the form of 2x minus x0 minus x1 divided by x2 minus x0, x2 minus x1 into f of x2. So, now if you will just differentiate once more here p2 dash x, then we can just obtain p2 double dash x also here. So, next if you will just go for the second differentiation of this function here, if you will just differentiate once more here, then we can just write p2 double dash of x, this can be written as, first one is the variable term only, this is involved here. So, 2 by x0 minus x1, x0 minus x2 into f of x0 plus 2 by x1 minus x0, x1 minus x2 into f of x1 plus the last term, if you will just take one more differentiation, it can just represent the term here x2 minus x0, x2 minus x1 into f of x2 here. And combinedly, if you will just write this term, this can be written in the form of like 2 is common for all the terms here, 2 divided by x0 minus x1, x1 minus x2, x2 minus x0 here. And if you will just write the upper part of the term here, this can be written in the form of like x2 minus x1 into f of x0 plus next term, if you will just see here, that is not common to this term here, that is in the form of like if you will just see, that is nothing but x0 minus x2, x0 minus x2 f of x1 plus last term, that is in the form of like if you will just see, that is in the form of x1 minus x0 here. So, x1 minus x0 f of x2. So, this is the complete representation of this second order differentiation of p2x. This means that if you will just involve only 3 points, then we can just represent this polynomial in this form. So, likewise we can just express the nth differentiation, or if you will just consider a polynomial of degree n also here, then the first order differentiation, second order differentiation, third order differences, we can just get it in the same manner here. So, based on this, we can just also say that if all these points suppose equally spaced, sometimes we are just saying that Lagrange interpolating polynomial, this can be applicable both for equispaced points and unequispaced points. In this case, we have just considered that all points may be unequally spaced. If we will just consider that all the points are equally spaced, suppose equally spaced means we can just consider x1 equals to x0 plus h, x2 equals to x0 plus 2h. So, likewise we can just say that xn equals to x0 plus nh here. Obviously, in a graphical representation you can just say that if x0 is the starting point here and xn is the end point here, if you will just divide this complete interval into n equal parts, we can just say that it is equally spaced or all the points are equispaced. So, if you will just replace all of these points by this transformation, then we can just obtain the first order differentiation p2 dash of x0 suppose. This means that we are just considering this differentiation at this point x0 here. If you will just consider that one, that can be written in the form like if you will just see, this one is the differentiation here. So, first point it can be written in the form of like 2x0 minus, suppose this differentiation we want to determine at the point x0 here. So, then x equals to x0 here minus x0 minus h minus x0 minus 2h divided by, this is x0 minus x0 minus h, this is x0 minus x0 minus 2h into f of x0 plus 2x0 minus x0 minus x0 minus 2h divided by x0 plus h minus x0, x0 plus h minus x0 minus 2h into f of x0 plus h plus the last term if you will just write here, that is as 2x0 minus x0 minus x0 minus h divided by x0 plus 2h minus x0, x0 plus 2h minus x0 minus h into f of x0 plus 2h here. So, if you will just cancel all the terms here, then we can just say that this x0 can be cancel it out, this x0 is cancel it out, this x0 is cancel it out here, this is 2x0, it is cancelled it out. So, this x0 is cancel it out, 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 this x0 is cancel it out. So, finally, if you just write all the terms here, we can just write p2 dash of x0 first, if you will just see here minus h minus 2h, here also minus h minus 2h. So, if you will just see here, we can just take common 1 by 2h from all these terms, and it can be written in the form of like minus 3 f of x0 plus 4 f of x1 minus f of x2 here. So, this means that all of the terms, if you will just see that first term, if you will just see here, that is in the form of like minus h minus 2h here. So, that is why this is minus 3h, and lower one if you will just see here minus h, so minus 2h, this one also minus 3h here, then f of x0. So, next one if you will just see here, so the same thing we can just say, that is a 2x0 minus x0, it is just cancel it out, then 2h is remained in the upper side here. So, then lower side if you will just see here, that is in the form of x0 minus x0, it is just cancel it out, then h remains here, then h minus 2h here. So, that will be minus h will be remained. So, minus h into h, that will just generate here h square. So, likewise if you will just solve these three terms, we can just obviously get this 3-point formula here, that is this is called the first 3-point formula for first order derivative here. Next we will just go for this second order differentiation here. So, if you will just differentiate this p2 double dash at x0, then we can just obtain here p2 double dash of x0 as directly the same formulation we can just use here also, that is 2 by x0 minus h, x0 plus h minus x0 minus 2h, x0 plus 2h minus x0 into x0 plus 2h minus x0 minus h into f of x0 plus x0 minus x0 minus 2h into f of x0 plus h here plus x0 plus h minus x0 into f of x0 plus 2h. So, if you will just see here, this x0 cancel it out, x0 cancel it out, x0 is also cancel it out here, this is also cancel it out, this is also cancel it out. If you will just write in a complete form here, then it can be written as 2y minus h, this one also here minus h, last one if you will just see here, this is nothing but 2h here. And inside these functions if you will just see, first one just gives you h f0, since x0 cancel it out, so 2h minus h, so that is why it is just giving you h here. So, h into f of x0, that is nothing but h f0 here. Second part if you will just see here, that is nothing but minus 2h here, that we can just write minus 2h f1, and last point if you will just see here, this can be just giving you h f of x2, and finally we can just write this one as, since minus minus it is just giving you plus here this one. So, f0, since h can be taken out common from all the terms here, so f0 minus 2f1 plus f2 divided by h square. Since we are just writing here f0 is nothing but f of x0 and f1 is nothing but f of x1 and f2 is nothing but f of x2. This is called second order forward difference formula. Especially if you will just see the same formula, you can just get it also in Taylor series expansion also. This is called second order forward difference formula. So, based on this differentiation, we can just go for the solution of some problems. First, we will discuss these problems based on this Lagrange interpolation, where it can be exactly applied to the nodal points. This means that either at x0 or at x1, directly if you will just put at that point whatever we have just discussed here, the same way we can just differentiate and we can obtain the solution. So, first if you will just consider this example, that is in the form like x is prescribed at 0, 2, 3, 4, 7 suppose, since we have considered as unequal spaced point, and if the functional values are expressed as 4, 26, 58, 112, 466 suppose, and the value is asked you to compute at x equals to 2. Since if you will just see these tabular values here, x equals to 2 is a particular tabular value on this problem here, and it is asked you to evaluate these values at y dash of 2. So, first if you will just discuss here, find y dash of 2 using the following data. Suppose the question is asked and the data points are given in the form like x at 0, 2, 3, 4, 7 suppose, and this functional values are expressed in the form 4, 26, 58, 112 and 466. This is suppose given here, and obviously we can just say that we have to find y dash of x at x equals to 2 here. Obviously 2 is nothing but the tabular point here, and if you will just use this Lagrange interpolation, then the formula can be written in the form of Pnx equals to summation k equals to 0 to 4, since if you will just see here 5 nodal points are there, so it can just generate a polynomial of degree 4 here. So, that is why you can just write Lkx f of x k here. and directly we can just write Lkx as omega x divided by x minus xk, omega dash of xk here, and omega of x can be expressed in the form of x minus 0, x minus 2, x minus 3, x minus 4, x minus 7 here, since all the points would be included in the numerator product part here. So, if we want to find this L0x here, so L0x can be written in the form like x minus x1, x minus x2, x minus x3, x minus x4 divided by x0 minus x1, x0 minus x2, x0 minus x3, x0 minus x4 here. And directly if you will just write these functional values in the upper part here, this can be written as x minus 2, x minus 3, x minus 4, x minus 7 divided by this all of these terms like 0 minus 2, 0 minus 3, 0 minus 4, 0 minus 7 here. And similarly, if you just write L1x, this can be represented in the form of like x minus x0, x minus x2, x minus x3, x minus x4 divided by x1 minus x0, x1 minus x2, x1 minus x3, x1 minus x4, and this can be written in the form of like x minus 0, x minus 3, x minus 4, x minus 7 divided by 2 minus 0, 2 minus 3, 2 minus 4, 2 minus 7 here. Similarly, we can just write L2x, x minus x0, x minus x1, x minus x3, x minus x4 divided by x2 minus x0, x2 minus x1, x2 minus x3, x2 minus x4, and which can be represented in the data points as x minus 0, x minus 2, x minus 4, x minus 7 divided by point is here 3 minus 0, 3 minus 2, 3 minus 4, 3 minus 7 here. Similarly, we can just define L3x as x minus 0, x minus 2, x minus 3 into x minus 7 divided by 3 minus, this will be 4 minus 0, 4 minus 2, 4 minus 3 into 4 minus 7 here, and L4x can be defined in the form like x minus 0, x minus 2, x minus 3, x minus 4 divided by 7 minus 0, 7 minus 2, 7 minus 3 into 7 minus 4. So, that is the representation for L4x here. So, if you will just consider the first order derivative based on Lagrange interpolation, then we can just express this p n dash x as, so we can just express p n dash x as summation k equals to 0 to 4 L k dash of x f of x k here, and if you will just define here L k x dash x as summation, or directly if you will just write here d by dx of omega of x divided by x minus x k omega dash of x k Then omega x is represented as, here if you will just see, that is a function of x only here, that is in the form of like x minus 0, x minus 2, x minus 3, x minus 4 into x minus 7 here. And directly we can just evaluate this derivative with respect to x for this function here. And obviously if we want to write, suppose at a point 2, suppose here, if you will just see the first function L0 2 here, so directly we can just say that since at a particular point we are just evaluating, if you will just see here L0x, which is represented in the form of like a x minus 2, x minus 3, x minus 4, x minus 7 divided by your 0 minus 2, 0 minus 3, 0 minus 4, 0 minus 7, this one. So if you just take this differentiation with respect to x here, that is just giving you at a point particularly 2, if you will just see here L0 dash of 2, this one. So then except first product, if you will just consider this one, this will just give you a non-zero value, and everywhere else wherever this x minus 2 is present for remaining all of these derivative terms, that will just give you a 0 term there. So that is why we can just write this complete product form here, that one as 2 minus 3, 2 minus 4, 2 minus 7 divided by minus 2 into minus 3 into minus 4 into minus 7 here. Since if you will just see this differentiation with respect to x minus 3, if you will just consider, then x minus 2 will be present, especially x minus 2, that will just give you 0 here. If you will just differentiate x minus 4 with respect to x minus 4, then x minus 2 is also present in the another term, so that will just give you a 0 value there. So likewise whatever this product terms, if you will just consider except x minus 2, then all other terms will be 0 there. So that is why this can be represented here in this form only, and the value if you will just calculate, that is just giving you 5 by minus 5 by 84. Similarly, if you will just calculate here L1 dash of 2, suppose next immediate calculation is L1x. Suppose if you will just see here, L1x can be written in the form of like x minus 0, x minus 3, x minus 4, x minus 7 divided by 2 minus 0, 2 minus 3, 2 minus 4, 2 minus 7 here. And if you just take the derivative with respect to x and put these functional values 2 there, so all these terms will exist here if you will just see. Since in the first differentiation, if you will just take this one, so we can just write this term as x minus 3 into x minus 4 into x minus 7. Second term, if you will just do this one, then plus x into x minus 4 into x minus 7. Then next term, if you will just take the differences with respect to x minus 4 here, then we can just write x minus 0, x minus 3 into x minus 7. And last term, if you will just differentiate, so all the terms at point 2 it will just exist, and in that case we can just write this one as L1 dash 2 equals to minus 6 by 5 here if you will just calculate. Then we will just go for like a L2 dash of 2. L2 dash of 2, if you will just see, again the same scenario it can happen. This means that if you will just calculate L2 of x, again this x minus 2 term will be there. So that is why except one term, all other terms it will just vanish after the differentiation here, and we can just write this differentiation as L02 dash of 2 there, and which can be written as like 12 by 20 by 12 here. So the value is coming as like L2 dash of 2, that is just giving you like 5 minus 5 by 3 here. Sorry, this is 5 by 3 only, and L1 dash of 2, this is just giving you minus 6 by 5. And if you, in the same manner, if you just compute here L3 dash of 2, that is the same way we have to treat here also, that will just give you minus 5 by 12, and if you just compute L4 dash of 2, that will just give you 1 by 105. Once all of these values are known to us, then we can just write this functional derivative. This means that we can just write y dash of 2 as L0 dash of 2 into f of x0 plus L1 dash of 2 f of x2 plus L1 dash of x3 f of x2 f of x3 plus L3 dash of 2 f of x3 and L4 dash of 2 into f of x4 there. So, if you just write all these terms here, the derivative of like this term y dash of 2, it can be written in the form like p n dash of 2 as minus 5 by 84, that is the first term, into f of x0, that is nothing but 4 here, plus 6 by 5 into this is minus 6 by 5 here, the value, into 26. So, next term is like 5 by 3 into 58, and immediate next term is like minus 5 by 12 into 112, minus 5 by 12 into 112 plus 1 by 105 into 466 here, and the computed values, that is just giving you here 23. If you will just see here, this means that we are just writing these values, that is in the form like L0 of 2 or L0 dash of 2 into f of x0 plus L1 dash of 2 f of x1, L2 dash of 2 f of x2 plus L3 dash of 2 f of x3 plus L4 dash of 2 f of x4 here. Or completely, if we will just write all these terms, then we can just evaluate this derivative or first order derivative for this function f of x by constructing a polynomial p n of x here. So, obviously based on that we can just evaluate these derivatives for all of these unequispaced points or equispaced points based on this Lagrangian interpolation formula. So, next lecture we will just consider this unequispaced points or some other examples based on this Lagrange interpolating polynomial. Thank you for listening this lecture.